All right, so next up in our kind of quest of really trying to explore a whole bunch of different techniques to try to show why a particular statement has to be true is this statement talking about perfect squares. So before we dive too far into this kind of example, I want to step back and just kind of remind you about this idea of what is a perfect square. So hopefully you've kind of seen the idea of what a perfect square is. This kind of goes back to elementary school or whenever you first learned about perfect squares. And when you first build these things, you typically just start by taking a number, squaring it, and then that new number ends up being a perfect square. For example, if you look at 0, if you square that thing, it's going to become 0. If you look at 1 squared, I know it's going to kick out a 1. If I look at 2 squared, it's going to kick out a 4. So in this case, you can see that 0, 1, and 4 are all perfect squares. Likewise, you can see that 9, 16, 25, those are all going to be perfect squares because they come from squaring 3, 4, or 5. So in this case, what's going to happen is that we can use that idea to actually motivate the official definition of what a perfect square is. So the idea is that if you give me some number, in this case, I'm going to call it x. I'm going to say that x is a perfect square, provided that I can find this other number, this little k, and this k is going to be connected to x in that if I square this k, it's actually going to give me x back. So in this case, the k that's going to go with the 0 is just the 0, the k that goes with the 1 is a 1, the k that goes with the 4 is a 2, the k that goes with the 3 is the 9, the 4 goes with the 16, and so on and so forth. Often we refer to this thing as being this square root or this principal square root, this thing that really creates this perfect square. Likewise, we're going to actually just make our lives a little bit easier by only restricting our attention to positive things. We know that if I look at the number 4, I could actually write 4 as negative 2 squared. But when I square that negative sign, it disappears, so it becomes kind of lost in translation. So all I want to do when I'm talking about perfect squares is only deal with positive things. Okay, so let's go back to our actual statement about what's going on, and then we're going to chat a little bit about how we can attack this thing. So in this statement, I'm going to be starting with 2 random integers. So the idea is that if I start with my favorite numbers, pick out whatever ones you want to, I'm going to call those things A and B. What's going to happen is I'm going to feed this thing into a conditional statement. What's going to happen in this statement is I'm going to say if the product of those two things, so that is A times B, is not a perfect square, so there's a big not coming into play here, what's going to happen is that neither A nor B were perfect squares to start with. So again, I'm going to have another negation happening over there, and there's this big OR that's going to happen in the middle of this thing. So before we dive too far, I'm going to convert this thing into this kind of logic symbols, the stuff that we're kind of bringing back to what we were doing in previous sections. So the idea is that I'm going to have this universal quantifier floating around because I have this idea that this is going to work for any A and B that I'd ever want to have. So in this case, I'm going to have for all integers A as well as for all integers B. What's going to happen is that if A times B is not a perfect square, so in this case, I'm using the predicate S of x to represent that x is a perfect square. So the actual statement's going to look like the negation of that. So it's not the case that A times B is a perfect square. If that's going to occur, what's going to happen is that either A or B are not going to be perfect squares. So again, I'm picking up those little negation operators out in front of everything as well. So in this case, this is my big overall statement, and I want to think a little bit about how do I show this thing to be true. As it stands right now, it's actually really challenging to show, and the reason for this is actually twofold. The first thing I'm going to see is actually that OR, and that's actually the biggest, most annoying thing in this particular example. What's going to happen is that I get to assume something about the product of A times B. But what's going to happen is that I can go one of 2 different paths. I could either go down this path where A is not a perfect square, or I could go down the path where B is not a perfect square. And that's challenging. I have to kind of think about, well, okay, I'm sitting with A times B and I don't really know what to do. It's either going to be this or it's going to be this. I'm not really sure. So that's annoying to work with. And we're going to see a little bit about how we can attack that. The second thing that's somewhat annoying is all of these nots. There's this notion of not a perfect square. We gave the definition of what it means to be a perfect square, but we don't really have a good definition of what it's not to be a perfect square. It's basically just, I can't find some number k that works out nicely. So in that case, both of those things go together to say, I don't really want to attack this problem as it is. I want to manipulate this thing to change it up, but I still want to keep this notion of equivalence. I want to just make it look a little bit nicer. So in this case, the actual mode that's going to come into play is going to be the contrapositive. This is actually kind of my gut reaction. Whenever I see something that I don't really like working with what I have right now, I try to hit it with a contrapositive. Often this contrapositive is going to change a bunch of things into something that's a little bit easier to work with. And those two things that were somewhat kind of awkward, the ors and the nots, get fixed really quickly when I have the contrapositive. Obviously, you can see that with the contrapositive is going to bring about negations because I'm going to switch my hypothesis and conclusion, but they're going to pick up negations. So in that case, those knots are quickly going to disappear, which is nice because now I'm going to be talking about perfect squares. But the big, really nice fact that's going to come into play is this De Morgan's law. In this case, I have this or over in my conclusion, but what's going to happen is that when I negate that thing, I'm going to use De Morgan's, and that or is going to become an and. And it's much easier to work with ands than it is to work with ors. Ors, I have this kind of, it could be one or the other. I'm going down kind of unknown paths. When I work with an and, I can say that two things are going to occur, and then they're going to feed into something. So that's what's going to be nice in this case, is that when I write down the contrapositive of this thing, the actual proof of this thing is quite short. And we'll see that in just a little bit. So first off, let's write the actual contrapositive of this thing. And I'm first going to do it in symbols and then just kind of spit out what the actual verbiage of this thing is going to be in kind of a plain English sentence. And that's actually going to be what fuels this kind of big overall proof. So in this case, I'm going to still keep my universal quantifiers around, which is always going to be the case in this case. I'm not changing any of that stuff. Okay, so now here's where my contrapositive is going to come into play. What's going to happen is that my hypothesis and conclusion are going to switch orders, but they're going to pick up negations. I know that I can't just switch the order of those things because that's going to be the converse, and the converse is not logically equivalent to the original statement. So in this case, what I'm going to write down here is going to be logically equivalent to my original thing, which is the big kicker in all of this, is that I'm not changing anything. I'm just changing the way it looks. I'm making it look a little bit nicer. So in this case, negating that conclusion is going to be a pretty nice thing. All right, and then I'm going to negate my hypothesis, which you're going to see is going to come out to be pretty nice as well. All right, so that's a parenthesis on there. I think I'm good with parentheses. All right, so I'm going to keep on bringing down these quantifiers, and now I'm just going to use De Morgan's as well as this property about double negation. So what's going to happen is that this negation operator is going to basically be kind of distributed across to everything. So in this case, I'm going to pick up a double negation on S of A, which is just going to turn into an S of A. Boom. S of A. The or is going to switch to an and this negation of this negation is again going to pick up this double negation. So I'm just going to have that B is a perfect square. So in this case, it's going to say I'm going to have A and B are going to be perfect squares, and that's going to imply that the product of these two things is going to be a perfect square. So that is actually going to be what makes this whole argument work, is that when I convert this thing back down into kind of an actual English sentence, the whole proof kind of writes itself already. So what's going to happen is that my original statement is logically equivalent to this contrapositive. That contrapositive is actually written as for all integers a and b. So I'm still starting with whatever a's and b's I want to. So in that case, that should be a b. What's going to happen is that if a and b happen to be perfect squares, then the product is going to be a perfect square. So this direction is way easier to work with because I don't have any of these knots, I don't have any of these ors, I have a nice and in the middle of these things, and everything is just chatting about perfect squares. So what's going to happen is that since a is a perfect square, a is going to look something like some number squared. In this case, it could be whatever random number I want to, so I'm going to introduce this kind of arbitrary letter. What's going to happen in this case is I could say maybe it's, I don't know, let's call it h squared. Likewise, b is going to be some perfect square, so let's go ahead and say b is going to be k squared. The kicker here is that they actually should be different letters. I don't want to say a is going to equal k squared and b is going to equal k squared because I could actually be talking about multiplying two different perfect squares. The idea is that I could be multiplying 4 and 16. Those are two different perfect squares, one of which is coming from 2, one of which is coming from 4. So I do want those properly to be different. But in this case, you can see that when I multiply these things together, a times b, what's going to happen is that I'm just going to get an h squared multiplied by a k squared, and if I kind of bring out that square, this is just going to be viewed as h times k quantity squared. And hey, now it looks like a times b is some random number squared. In that case, that's going to tell me that a times b is a perfect square. And that's it. That's the whole proof. The kind of guts of what makes this all work is going to be converting that initial statement into the contrapositive, doing this De Morgan's, doing this kind of cleanup. It's why we spent so much time back in chapter 2 just looking at things, writing down negations, writing down contrapositives, seeing these kind of different statements kind of come together, because once I make that switch to the contrapositive world, the actual proof is really pretty easy. So if I want to actually clean this thing up and write it as a nice kind of paragraph, what I'm going to do is again tell the reader right away, hey, I'm switching things up. I'm using one of these kind of indirect proof techniques. In this case, I'm using the contrapositive. So I'm going to prove this result using the contrapositive, and I might as well just go ahead and tell the reader right away what the contrapositive is. So in this case, the contrapositive of the original statement, which is again going to be logically equivalent to the original one, is going to say, for all integers a and b, if a and b are perfect squares, so again there's no negation in there, then a times b is a perfect square. Again, no negation in that thing as well, and I picked up the and. And now I'm just going to basically just formulate what I just got done saying. The idea is that a and b happen to be perfect squares, so there's going to be some integers, call them h and k, such that a is going to be h squared, b is going to be k squared. If I multiply these things together, so if I take a times b and multiply them together, it's going to introduce h times k quantity squared. Since this random thing, h times k, is still going to be an integer, because an integer multiplied by another integer is still going to be an integer, it's going to follow that a times b is in fact going to be a perfect square. And that's it. That's kind of the nice kind of, if you can sketch out the horrible argument over here, it's relatively easy to convert it into a somewhat easier to digest paragraph. So I mentioned at the very beginning of this thing that it is not an if and only if statement. It is a classic if-then, just a conditional statement. What's happening in this case is that this thing is not biconditional. The reverse direction does not work. And the reason for that is because I can find two numbers that are not perfect squares, but the product of them happens to be a perfect square. So the example in this case is pretty easy. You just take a to be 2, you take b to be 2. Those things are most certainly not perfect squares because I don't have 2 as the square of any integer. It's just a 2. But if I multiply those things together, a times b is going to be 2 times 2, which, hey, is 2 squared, is definitely a perfect square. It's a 2 quantity squared, therefore it's a perfect square. So in this case, it is classically just a conditional statement. I cannot do any better than what it's currently written as. So kind of earlier when we first started looking at some of these direct proofs, I gave you some conditional statements, which actually were biconditional statements. And that's what those previous two videos were looking at is, hey, I actually can go back, clean those things up a little bit and say, oh, the reverse direction is also true. In this case, the reverse direction is not true. I cannot go backwards on this one. I'm only stuck going in the forward direction. So in this case, the way we attack this one is by using what's referred to as a contrapositive. In the next video, we're actually going to be chatting a little bit about an alternative approach to this thing, which is going to be using this idea of negation. What's going to happen is that I'm going to write down the negation of this thing and say, actually, the negation is complete garbage. It's completely false in this case, therefore the original statement must be true. And what that is, it's going to be referred to as a proof by contradiction. So in this case, it'll look really similar to the one that we have right here, but it's got a little bit more kind of subtlety kind of underlying a lot of it. It's still going to be referred to as an indirect proof, just another version of it.